All right, welcome to the third video for topic 1 of week 10, where we're going to cover a few questions relating to the topic content, so heat and calorimetry, covering both sensible and latent heats, potentially. I can't remember which questions I've written, so we'll find out in a moment. As usual with these videos, please do pause the video if you haven't already had a go at the questions. Do try the question yourself. You're not going to be able to know whether you can do it just by watching me do it and going, oh yeah, that makes sense. Have a go. That's the most important thing. Most important thing with physics in general is have a go at thinking about and solving these problems. The temptation is to just watch and say, yep, that makes sense. But when you come to a test or an exam or just a general life scenario where you want to try and apply these concepts yourself, it becomes very difficult. So we are looking at the lecture slides for week 10.1. Oh, I just noticed I haven't updated the number on the lecture either. It's 10.1, not 9.1. So we'll jump into the questions. We had the long example, which we worked through in the last video. Now we've got quite a few questions. What is it? 3, 4, 5 questions here to deal with calorimetry. Again, that's just because this can be quite a difficult concept, quite a difficult process for people to really understand. So we want to try and drill that home as much as we can. Question 1, lead vat. You have a 20 kilogram vat made out of lead. How much heat input is required to raise the temperature from 10 to 90 degrees C? And then the vat starts again at 10 degrees C. And now it's filled with 20 kilograms of water. How much energy do we need to raise the temperature of the vat and water to 90 degrees C? So we've got two different scenarios. Just a vat on its own, made of lead, and then a vat of lead made filled with water. And we have to raise the temperature in both cases to 90 degrees Celsius. And we want to know what the final heat input required is in both cases. So nothing too strenuous for this one. There's no phase changes. There's no nothing funny going on. We've just got a simple calorimetry question for lead and water. Now, as you'll notice on the slide, it did give you some values, which I'm going to write out in a moment. If you haven't already, pause the video, have a go at this. I'm about to work through the answer, so let's see what we've got. We've got the mass of the vat is 20 kilograms. And we know that temperature initial is 10 degrees C, temperature final is 90 degrees C. So our change in temperature is equal to 80 Kelvin, or 80 degrees C, but I'm going to stick with Kelvin. You'll notice that I often tend to do that. I just jump into Kelvin whenever I'm talking about a temperature difference. If you're more comfortable with degrees C, remembering that they're the same thing, that's fine. I just tend to stick with Kelvin myself. So that's our initial scenario, and obviously we then need to know the C for the vat, the specific heat capacity for the vat, which is obviously the specific heat capacity of lead. And according to the table on the slide, that is in joules per kilogram per Kelvin, 130. So if we've got 130 joules per kilogram per Kelvin, we've got to go 20 kilograms and 80 Kelvin. So we're going to have Q is equal to 20 kilograms times 130 joules per kilogram per Kelvin times 80 Kelvin, and that will give us our result, which is 208 kilojoules. If my previous calculation was correct, feel free to check that and call me out in the stream forum if I've done that incorrectly, but that's what I get out. I get out 208 kilojoules for the heat required to raise the temperature of the vat from 10 to 90 degrees Celsius. The next part of the question is exactly the same, except that we're dealing with two components. We've now got mvat is still the same, 20 kilograms. We've got the delta T still the same of 80 Kelvin, and we've got the C of lead is still the same, which is, what did we just say, 130 joules per kilogram per Kelvin. And now we've got to do the water as well. So M water is also 20 kgs. We've got delta T for water is the same, 80 Kelvin. And C for water, which you may start to memorize because we use it quite a lot, 4186 joules per kilogram per Kelvin. So we've now got both of these to consider. So the total heat is just going to be the heat required to warm the lead up and the heat required to warm the water up. Now we already know Q for the lead is 208 kilojoules. And now we just do the same thing for this, for the water. And it's easy when we've got something like this with no phase changes, just multiply them. You've got 20 kilograms and 80 Kelvin, and it takes 4,186 joules per kilogram per Kelvin. So you just multiply these three numbers all together. And for that, we get out 6,698 kilojoules, which is 6.7 million joules, right? Keeping track of those units. But I'm keeping it in kilojoules because it's just simpler for me to write out. And so adding those together, we see that we get 6,900 kilojoules. That's only the 2SF. It's obviously not quite that if you go more, but our initial values are all 2SF-ish anyway. So we have 6,900 kilojoules for both the vat and the water. The interesting thing to note, which as we've hopefully made clear, it should be no surprise by now, is that when we add the water in, it takes a lot more energy. Right? The water took 6,700 kilojoules, 6.7 million joules. The lead only took 200,000 joules. And that's the same mass of each. They're both 20 kilograms. But the water took so much more energy than the lead to go up the same temperature. And that's because of the different specific heat capacities. That was the only difference. We both had 20 kilos, we both had 20 kilograms, we both had 80 Kelvin, but the specific heat capacity is very different. So remember that that's because they put the energy into different parts of their internal energy. You give them some heat, they put them into different places. So what that tells us is that for lead, you give it some energy, right, and a big chunk of that is going to go into temperature, and then smaller bits are going to go off into the other parts, right? So a big chunk is going to go into temperature. So for that to go up to 80 Kelvin, you only needed 200 kilojoules. I'm rounding quite a lot now, 200, that's just the nearest 100, but you get the idea. So 200 kilojoules, and that raised the temperature by 80 Kelvin. But for water, only a tiny amount of it goes into temperature. So if we still want that to be 80 Kelvin, right, that's only a little fraction. Here, that was more than half. It's a pure guess, I don't actually know, but it was a big chunk of our energy. It might even be most of it. We could calculate that if you wanted to by going back to the kinetic energy of particles, thinking about how many particles there are in a kilogram of lead versus the specific heat capacity. You could calculate how much actual fraction it is, but we've got a big chunk of it going into energy, into translational kinetic energy, so we don't need too much energy. But over here, water puts so much of it into other forms, right? It puts lots into rotational, vibrational, and chemical bonds. I don't know all the exact ratios, but you can imagine it doesn't really matter too much. All that matters is this one, right? For temperature to be 80 Kelvin, you need a whole lot more energy coming in, right? And in this case, it was 6.7 million Kelvin, or megajoules. So you needed 6.7 megajoules to get a 80 Kelvin rise out of water, and you only needed 200 kilojoules to get an 80 Kelvin rise out of lead, because it puts a lot of it into temperature, whereas water only puts a little bit into temperature. So hopefully that makes a bit of sense, helps reinforce those ideas of specific heat capacities and what's actually going on in the system. But that is the first question. Jumping back to the slideshow now, we've got another question. You're making a soup for lunch using a small immersion heater. So an immersion heater, if you're not familiar with that word, immersion, which means you submerge it, you put it underwater. So this immersion heater, you're putting it inside the soup and applying heat directly inside the soup. It's rated at 350 watts, and it's asking how long will it take to heat 1 cup of water for your soup from 15 degrees C, so that was the temperature of the cold soup, and you're trying to heat it up to 75 degrees C. How long will it take? So first thing first, have a go, pause, think about it. If you're not sure how to even start, I'm going to give you a little hint now, and this hint will hopefully get you started, and you can then have a go, and then I'm going to solve it. So the hint is remember what we mean by power. When we talk about 350 watts, we're talking about 350 joules per second, right? A watt is energy per time, joules per second. So with that little hint, you might be able to solve it now if you were stuck to start with. Now that you've had a go, hopefully everyone's had a go at this now, we're going to work through and see if we can solve the question. So as usual, jump back to document camera. Here we go. We've got 1 cup of water. 1 cup of water equals 250 mils, right, or 1/4 of a litre. And hopefully you'll remember that there's multiple ways to think about it, but generally 1,000 litres makes up a cubic metre. So that'll be 0.25 times 10 to the -3 cubic meters. You can then use the density of water, or you may also remember that 1 litre equals 1 kilogram. So it's actually going to come out the same there. 1 litre of water is 1 kilogram of water. So what we have is 0 m of soup is equal, I don't need the subscript actually because there's nothing else going on, we've just got the mass, is equal to 0.25 kgs. We have the initial temperature is equal to 15 degrees C, the final temperature is equal to 75 degrees C, which gives us a delta T, a change in temperature from 15 up to 75, which is 60 Kelvin. And our heater has a power of 350 watts, right, which equals 350 joules per second. So there are 2 steps to this question. The first is to figure out how much energy we need. Right, so how much heat do we need? Right, and remember that that's in joules. And then once we know how many joules we need, if we're getting 350 joules per second, we know that it's just going to be Q over P. Right? So however much energy we need divided by 350 joules per second will give us our answer in seconds. So that's it. We've got to figure out these 2 things. And Q is pretty straightforward. Q is just the same as we've always had. This time was really the trick on this question. So the Q is just equal to C times M times delta T, and we've got all of that. We've got C for water, which I haven't written down, but we all know it. We all remember, hopefully, seawater 4186. We'll always be given that. If it was different, it would tell us. So again, we're assuming the soup behaves enough like water that we can just use this value, joules per kilogram per Kelvin. So we've got that for Q, which if you plug in those numbers, 0.25 times 4,186 times 60 Kelvin, we get 62,790 joules. And we've said that we get 350 joules per second. So if we divide 62,790 by 350, that'll tell us how many seconds it takes to heat up our soup. And that is 179.4 seconds, which is, quite a few seconds. But if you turn that into minutes, it is going to be 179. So we have 60 seconds in a minute. So 3 minutes would be 180. So it's pretty much 3 minutes. And that's not too bad. If you think about a microwave would take a couple of minutes to heat up a soup, and here you've got a little immersion heater, which does it in pretty much the same time frame. So that's that question. As I said, the Q, pretty simple, just figuring out the same heat calculation using a specific heat capacity of water. There's nothing confusing there. This was the one that might have tripped people up. And again, it just comes back to remembering the definition of these terms, remembering that power is just energy per second. That's all power means, energy per second. So if you know how much energy you're giving out per second and you know how much energy you need in total, then you can figure out how many seconds that will take. So a little bit of a trick on, not a trick, but a little bit of a twist on that one compared to what we're used to, what we've seen in the other examples. So moving on to the next question, silver and water. You have a 250 gram block of silver that has been heated to 140 degrees C you drop it into a bucket full of water, which is 9 litres. There we go, 9 litres straight out of the tap at 21 degrees C. So just room temperature tap water, 9 litres of it. Determine the final temperature of the bucket silver system once thermal equilibrium has been reached. Right. So this is, if you remember that, if you watched the long example video from the second part of the second video, then we did a more complicated version where we had ice that was melting and we had phase changes. This is simpler than all of that. This is just 2 objects changing temperature. So it's actually just going to need our consideration of energy loss without changing phase. So just sensible heat. Again, understanding the physics is important. Yes, you've got all the information you need to just plug in some numbers into some equations and get some results out. But it's really going to be beneficial if you understand the physics, understand what's going on. So we've got some block of silver, and it's at 140 degrees C. And we're putting it into a bucket of water, which is 9 litres of water, and it's at 21 degrees C. So we're putting that into there. And we want to know what's the final temperature. The key thing to remember is that we haven't been told anything about heat loss to the environment, so we're assuming overall this is a closed system. If we consider everything, it's closed. But of course, to understand what's going on between the 2 parts of this, the setup, we need to think about them individually. So we've got, this is an open system of our silver, and this is an open system of our water. And so we know that the Q lost by the silver is going to be equal to the Q gained by the water. Now, technically, we should put a negative out the front because it's lost. And then we'd say that that is the equal and opposite to the heat gained by the water, which means we'd end up with a negative on both sides, which is why I often just skip that. But just thought I'd mention that since I didn't mention it during my big long example earlier. So we have the Q lost by silver is equal to the Q gained by the water. There's no phase changes to go on. So all we have to worry about is these 2 components, these 2 equations. And of course, we all remember that Q is equal to C times M times delta T, and this is for silver. And that is equal to C for water times mass of water times delta T for water. Now, unlike the lead vat question, where we were given delta T and they both changed by the same delta T, here the delta T thing is going to be different on both sides, because the silver is dropping from 140 to some middle temperature, and the water is going up from 21 degrees C up to some temperature. And that some temperature has to be the same for both because we're reaching thermal equilibrium. So we don't know what these 2 values are, but we do know that the water is going to end up at some final temperature. So it's going to be final temperature minus 21 degrees C. That's for this. And this is going to go from 140 degrees C down to some final temperature. And that final temperature is the same as this final temperature. So those are our 2 equations. And we now know everything to put in here apart from that final temperature so we can solve for it. So if we just do a bit of math on that, so that's the physics done, right? The physics was understanding this, understanding the system, thinking about what's happening with the energy conservation, energy going out of the silver goes into the water, and therefore we need to equate these 2 equations. That's the physics done. Now we're on to the maths. So the maths is just saying that we've got, if we expand this bracket and that bracket, we get 140 CSMS minus TF CSMS is equal to TF CW MW minus 21 CWMW. So we have, we can bring the 2 TF terms over to one side. It doesn't matter which. Probably makes more sense to move it over this side because then everything's positive, and bring this over this side. So I'll just do that in another color to try and be clear. I'm going to bring this over this side and then bring this over this side. but I'm also going to write it the other way around. So I'm going to write the TF terms over here. So we get TF of CSMS plus TFCWMW is equal to 140 CSMS minus, oh no, plus because we're moving it over, 21 CWMW. And so now you can hopefully, if you wanted to, again, you could do this as calculations. You could go and actually put in all the numbers earlier and do a bunch of calculations. But it's a good habit to get in to be doing the algebra if you're comfortable with it. So we can see that we can factor out this TF. We get TF is equal to TF times CSMS plus CWMW is equal to that whole thing. We don't have to change that at the moment. CSMS plus 21 CWMW. And then we can divide both sides by this bracket, right? So that bracket will cancel out on that side. We'll end up with CSMS plus CWMW on that side. And now we know everything here. That's just, we've got both of the specific heat capacities twice and both of the masses twice, and that will give us our solution. So at this point, you just plug in all your numbers and get your resulting temperature. And the final temperature should, if you've done everything correctly, I'll do it in another color, should come out to be 92.9, which is 93 degrees Celsius. So the final temperature of this is going to be 93 degrees C. All right, so as I said, physics, understanding what's going on, and then math, playing with the equation. And if you wanted to do this by putting the numbers in earlier and simplifying that a little bit with just numbers times TF, that's fine. I prefer the algebraic approach. It is more versatile, so it's good to get in the habit of doing that if you can. But if you feel more comfortable doing it by plugging in all the numbers, it's not necessarily wrong, but do be careful for rounding errors. All right. I've still got some more questions to go. As I said, quite a big topic. We want to cover off a lot of bases as much as we can without these. This question is, there's no actual calculation to do. It's more of a discussion question. Which will cause more serious burns when applied to skin? Steam at 100 degrees Celsius or water at 100 degrees Celsius? So you've got steam and you've got water. Now, water is implied that it's liquid, since that's what we tend to call water. If we say water, we don't normally mean steam or ice. We mean the liquid. So we've got steam at 100 degrees C or water at 100 degrees C. We're applying each of them to skin, which is going to cause a more serious burn. Don't practice this. Don't go and test it out. It's just a hypothetical question. Please don't make it a practical one. Which is going to be worse? Again, have a think about it. Try this yourself. Don't just rely on me explaining it in a moment, which I'm about to do. Do have a go first. Try and come up with your own explanation. Even if you're wrong, it then gives you a something to base your new information on. The information that I give you can be incorporated into your thought process, and you can see why you went wrong. It's a far better learning experience than just being told. So all of that said, what's going to be worse? There's a few assumptions to make, but everything else being the same, if everything else about the system is the same, then the steam will be worse, because at 100 degrees C, the water, if it gives off any heat, it will start dropping in temperature. And if we're applying it to skin, our assumption would be that we put the water on the skin and it has to go from 100 degrees C down to the same temperature as the skin. And so that's just going to give off however much energy it needs to drop down to that final temperature. However, steam, if you put that on the skin, it has to first change into a liquid. It has to condense into a liquid, which means that you have to bring in the latent heat of vaporization to turn it into 100 degrees Celsius water first, and then it's going to go from 100 degrees Celsius water down to the final temperature of water. So it still gives off that same amount of energy as the water did from 100 down to the final temperature, but it's also got this latent heat of vaporization that it's giving off first. It's giving off more heat in that first phase change, and then the same heat during the temperature change. So that means that the steam is actually going to give a far worse burn. However, that is not always true in real life scenarios, because that assumption is that you have the same amount of matter. You have the same number of molecules of steam as you do of boiling of 100 degrees Celsius water. And that's not always a very good assumption. In real world, that's a very poor assumption because steam is very much less dense than water is. Water, we all know, is, it's a liquid. It's a kilogram is a liter. For steam, it's a lot less dense. And if you're in atmospheric pressure, it's going to pretty much expand to be a similar density to air, which is only 1 kilogram per cubic meter. It would be a bit higher because water molecules are heavy, but it would still expand to be very low density. And of course, being hotter than the surrounding air, it would be even lower density. So it's overall steam is going to be very low density. So we'd have to have a lot of steam, a large volume of steam, to have the same number of molecules as you would for the similar mass of water. And realistically, in a real life scenario, steam is going to be far fewer molecules. So even though each one gives off a lot more energy, the heat given off by each molecule of that gas as it turns into a liquid and then cools down is more than each molecule of the water. But there are so many more molecules of the water that you could get far worse burns from the water in reality. So all of that said, steam is worse on a per molecule basis, but if you think about the real life application, 100 degrees Celsius water is generally going to be worse because there's going to be a lot more of it. Jump back to the slides. As I've said there, same answer as I've just given, but typed onto a slide. And I think this will be the last question. The question here is ranking the following 4 scenarios in terms of least to most heat required. So again, no calculation, just a bit of thought. We've been given a table with the different specific heat capacities here, and you just have to try and think about which of these is going to need more or less heat. Now, yes, you could do the actual calculations. You're welcome to do the calculations, but you should hopefully be able to see just by looking at these numbers and not actually doing the calculation what the result would be. So again, have a go, do it now, pause the video if you need to, do whatever you need to do, and then restart and we'll get stuck into the solution. So our solution, I'm not going to go to the document camera because again, we don't necessarily need to do the calculations in full. We can, it's so easy that we can do it because we've got 1 kilogram and 2 kilogram and half kilograms. They're very simple numbers to deal with. But what we can look at is, let's start by looking at A, heating 1 kilogram of mercury by 1 degree C. That's the definition of a specific heat capacity. So the specific heat capacity of mercury is going to be our solution here. It's just that we're cancelling out that kg in degrees C. So mercury would need 140 joules for that. Officially, we just did a calculation. We multiplied 140 by 1 and then by 1 again. But it just came out to be 140. So 140 joules is for A. For B and C, I'm going to leave them for a second, go straight to D. Heating 2 kilograms of lead by 1 degree C. If 1 kilogram of lead needs 128 joules, then we're going to need double that to heat 2 kilograms. So it's going to be double 128, which we know is going to be more than 140. Without even doing the calculation, we know that D is going to need more heat than A. Now let's think about B and C. B, 1 kilogram of water by 1 degree C. Again, just like we saw with the mercury, that is the specific heat capacity. It's specific heat capacity times 1 times 1. So it comes out numerically to be the same value, but now just joules. And for water, that's 4,186. We just saw mercury was 140 joules. Lead was double 128, which if you've done it in your head, you'll know the number. But even without that, we know it's more than 140, and it's clearly less than 4,186. So that means that B is going to be the biggest out of A, B, and D. And now we have to think about C. We've got half a kilo of water and 2 degrees Celsius. Now think about specific heat capacity. It's saying how much energy per kilogram per degree Kelvin. If we only take if we've got 1 kilogram and we go up by 1 Kelvin, that'll need 4,186 joules. But if we halve the amount of water we've got, and we still give it that same amount of energy, it would go up by 2 Kelvin instead. So C and B are actually exactly the same amount of energy. In B, all the energy has gone into that 1 kilogram of water and gone up by 1 Kelvin. In C, you've got the same amount of energy, but there's now half as much water, which means each molecule is going to get twice as much heat, which means it's going to end up doubling in temperature compared to B. So they're actually the same. The heat is exactly the same for B and C. So we've got B and C is the same, and it's way bigger than both A and D. and then A was smaller than D because D was double 128 and A was only 140. So in ranking them from least to most, we have A is the least, then D, and then B and C are the most, and they are equal. And as you'll see on the final slide, that should hopefully be the same answers. Least is A, then D, then most B and C. So that brings us to the end of the lecture, the end of the content for topic 1 for week 10. As per the warning at the start, this did end up being quite long. We had 3 videos, each of which were fairly lengthy on their own. Put them all together, that's a lot of material to cover, but topics 2 and 3 should hopefully be a little more succinct, a little smaller for you to work through.